Hello and welcome. My name is Dr. John Hoagland, and this is my continuing series in mathematics. I'm with Provenance Geosciences. I'm teaching the mathematics to try to amplify some of my geological courses and geological consulting with Provenance Geosciences, and I also run a nonprofit, Carbon Negative Water and Energy. Today's topic is the Pythagorean Theorem, and more specifically, I want to do an interesting proof of that theorem. The Pythagorean theorem is presented to students very early on. And they use it, but they don't necessarily see a proof of it until much later, maybe not even at all. I'm not sure if I can recall getting a proof of it or not. So what is the Pythagorean theorem? It's used with a right triangle. They're shown on the right-hand side of the screen. Lettering conventions, though I won't be strictly following these, not that important in this proof, but usually you label the angle as the same as the vertex. You got the vertex A, the angle on that side is A, and then the side opposite of that is subscripted with a lowercase a. So you'll see angle A, opposite side of that is side A with a small letter A. Angle C is the right angle, the 90-degree angle, and the opposite side of that is the hypotenuse. And then B, the angle B at the top, and the opposite side is the base of the triangle. So the Pythagorean theorem relates the distances of the two legs, which are A and B, and the hypotenuse, which is C, of a right triangle. And to be clear, it only works for right triangles. Don't be trying to do this on other triangles. And again, on the notation, A is one leg. It can be the short or the long one. It doesn't matter. But then, of course, B is the other one. So short or long, or they might be equal in length with a 45-degree angle, 45-degree right triangle. The two legs are equal. But C is that hypotenuse. It's the longest of all three sides. It represents the shortest distance between 2 points. So the shortest distance between A and B is a straight line. But that shortest distance, that straight line, is longer than each of the square directions. So if I walk the corner, each corner, each block that I walk towards the corner is going to be shorter than the hypotenuse if I were able to walk directly. But obviously C is the shorter distance if I add up A and B. So the formula that relates those is the Pythagorean theorem, and most people have seen it before. A squared plus B squared equals C squared. So if the one leg is squared, multiplied together, that is A times A, and the other leg is squared, multiplied together, B times B, B squared, and you add those together, that's going to represent the length, that's going to be equal to the length of the hypotenuse, C squared. So where most students get this right off the bat is the distance formula. So most classes start the Pythagorean theorem with the distance formula because they're wanting to start using the Pythagorean theorem to prove lengths of sides of figures and whatnot, calculating slopes of lines and everything else. First of all, so if we take the distance between 2 points, so we have one point x1 and y1, might be the point -2, 1, and then the other point is on the right hand side there, 4, 3. So x is 4, y is 3 on the second point. On the first point, x is -2 and y is 1. So those represent 2 points, and they're given in the ordered pair in parentheses x1, y1, x2, y2, and the general sense of the formula is the difference between the x's squared plus the differences in the y's squared. Now that's under a square root sign because in this case the hypotenuse distance, which is the red line that we're after, that distance then would be d squared. You can see how each of those, the change in x direction and the change in y direction, forms legs of a right triangle in our Cartesian graph space. And then that's going to be equal to d squared. But the d, rather than d squared, we're solving it as d. So we take the square root of that entire sum over on the right-hand side. And that's the Pythagorean theorem. So just chasing this through using the 2 points. So we have the second point, the x is 4, and the original point, the x was minus 2. So we have 4 minus a negative 2, and so we're going to square that. And we're going to add that to 3. The changes in y is 3 minus 1. Remember, y is the second point in the ordered pair. Square that. So we end up with 6 squared plus 2 squared. And then just continuing on with another equal sign on that right-hand side, it's the square root then of 36 plus 4, or the final answer is the square root of 40. So this is used in math a lot to get distances on graph paper, but we still haven't proved. How do we know then that a squared plus b squared equals c squared, or in this case d squared? How do we know that that's the case without using the formula to prove it? So we start with a square, in this case a blue square, but I'm going to be a little bit tedious here. I'm actually going to prove that that's a square, go through some more geometry to prove that blue square is a square. And we have a square inside of it. We're going to also prove that red square is a square. And my understanding is that Pythagoras proved this in the Socratic method, even though he died 100 years before Socrates was born. But my understanding is the teaching method, maybe we should call it the Pythagoras method, because he taught the same way, that he'd have his students outside and he would be discussing whatever the topic was for the day, and he'd prove it and have discussions and questions and answers and challenges and whatnot. Kind of like an open discussion type of class where he would present and lead. And my understanding is that he was outside with his collection of students, and they were sitting in the sand, and he drew 2 squares in the sand. And I found this proof, and I thought that was unique, that there was like one arrangement here, and this is the arrangement that he used. But talking to some math friends of mine, they say, well, there's probably 100 different proofs for the Pythagorean theorem. So exactly which figure is the one that he used, don't really know for sure. But I think this is the idea anyway, that he 100% visually. So my tedium in proving things are square first is something he wouldn't have had to do. He would have just measured the sides. But let's go ahead and do this. And this is where, again, geometry and algebra get mixed up, because now we're going to mix together in the way things are taught these days. Because now we're going to use algebra and slopes of a line to prove that 2 lines are right angles. That's a different way of teaching. But at any rate, so we have the slope of, let's look at the lines on the blue square now. The segments on the blue square is OB and EG. They're the left and right side of that. Quadrilateral, it's a 4-sided figure. We know nothing about it. Let's assume we know nothing about it. And both of those slopes are infinite. They both have a rise of 7 and a run of 0. So that when you divide by 0, you get an undefined number. And so they're both infinite slopes. And because they have the same slope, both are infinite, we say that those slopes are parallel. So we know that because they have the same slope, they're parallel. OB and EG are parallel. Now let's look at the top and bottom. The segment's BE on the top and GO on the bottom. And they're both 0. They have a rise of 0 and a run of 7. So those are both slopes of 0. So because they have the same slope, they're parallel. And thus we know now that the blue OBEG figure, the blue quadrilateral, is a parallelogram. Continuing on, we're not going to conclude too much. We only know now that it's a parallelogram. So now we look at the slopes of the OB and BE segment. So the OB is the left-hand side of this parallelogram, and BE is the top of it. And how do those lines meet? Well, OB, as we already said, has got a vertical slope, and BE, as we've also already said, it's got a zero slope. So the slope is, again, 7 divided by 0 for OB, which is infinite. And then the slope for BE is 0 divided by 7, which is 0. So when we have a vertical slope, or an infinite slope, next to a zero slope, we know that those lines are perpendicular. So now we've concluded that OB and BE are perpendicular, meaning they form a right angle, And similarly for slopes BE and EG, BE is 0, and it's against the vertical slope for EG, so thus we know that BE and EG are perpendicular. So now we know that the blue quadrilateral is not only a parallelogram, we know that it's a rectangle. We move on from there, further classify this beast. So now we know that the blue quadrilateral is a rectangle, and we want to go one step further and prove that it's a square. And of course we knew this, but you never assume anything in geometry, you prove it. So the first thing we do is we look at the sides, and we just label the sides O to A, we're going to use A to B, we're going to use B, B to D. I'm skipping C and I'm using D. There's a reason for that, a method to my madness. And then etc. all the way around, E, F, G, and H, and I. And if we look at those segments around, now we just went clockwise around from the origin O all the way around to back to O again. When we look at that, those sides alternate between length 4 sides and length 3 sides. And so now that we have these alternating sides of length 4 and 3, we replace the labels, the A, B, C, D, E, F, G, H, I labels with A, B, A, B, A, B, all the way around the quadrilateral, all the way around. And we see that A is the 4 length and B is the 3 length. And then, of course, we look at the sides of the blue rectangle. We've established now that it's a rectangle, and we notice that OB is obviously the sum of the two segments, OA and AB, and then again all the way around. The sum of the 4 and the 3 sides all add up to 7. And we knew that. The blue figure is the blue rectangle is a square. But again, we make sure that we prove it rather than just accept it. And Pythagoras, standing out by his figure in the sand, would have obviously had his students measure that. And they would have said, yes, okay, it's 7 all the way around. So all 4 sides of the blue rectangle OBEG are equal, thus OBEG rectangle is a square. And now we got to look at the red square. We, again, don't accept anything on face value that it's necessarily a square. We're going to prove it first. And how are we going to do that? Well, now we look at the slopes HA, kind of approaching things the way we did with the blue square. Let's look at the slopes first. That's how we do it here now, and using kind of algebra graphing technique to prove the geometry. So the slope of HA and DF are both equal. There's a, if you go from H to A, there's a rise of 4, but a run of -3. Going the other way from D to F, there's a rise of -4 and a run of 3. So depending on whether you want to put the minus sign in the numerator or the denominator, depends on how you want to look at the slope. But either way, they're both -4/3. The slopes are -4/3 on the HA. So because they have the same slope, -4/3, they're parallel. And likewise, we look at the slopes of AD and HF, and we see that those are 3/4 The rise is 3 and the run is 4 in both cases. So those sides are parallel. So now we know that the red quadrilateral ADFH is a parallelogram. Well, at least that has the sides parallel. And again, moving along, we still have those segment lengths up there. A is 4, B is 3. Now we're going to look at the consecutive sides, HA and AD. And we're going to see that they're reciprocal and opposite. So for HA, we see that it has a rise of 4 and a run of minus 3, so it has a slope of minus 4/3. And the slope of the AD, however, it's got a rise of 3 and a run of 4, so it has a slope of 3/4. You'll see that those are reciprocal of each other and they're opposite signs. So reciprocal and opposite slopes means that HA and AD are perpendicular. And likewise, we do the same for the slopes of AD and the next segment, the next consecutive segment DF. And we see that they're reciprocal and opposite. AD has that rise of 3 and run of 4, so its slope is 3/4, and DF has a slope of minus 4 with a run of 3. Minus 4 rise and a 3 run, so minus 4/3. And again, those are reciprocal and opposite. So AD and DF are perpendicular. So now we've got the quadrilateral with parallel sides and perpendicular corners. We know that the ADFH quadrilateral, the red quadrilateral, is a rectangle. We still have to prove it's a square. So how do we do that? So now we look at the diagonals, and we cross the diagonals across the figure like that, and we look at their slope. And the slope of the diagonal HD and the diagonal FA are reciprocal and opposite. So we prove ourselves that. Looking at HD, it has a rise of 7 all the way across. The rise is all the way across the rectangle from the bottom to the top, and the run is 1. And meanwhile, if we look at the slope FA, it has a rise of 1 but a run of -7, or if you'd rather, a rise of -1 and a run of 7. Either way, it's got a minus sign in either the numerator or the denominator, but the slope is 1/7, -1/7. And those are reciprocal and opposite. So the diagonals, HD and FA, are perpendicular. So now we've got a quadrilateral with equal sides and perpendicular diagonals. The quadrilateral can either be a rhombus or a square. But because we know that it has 90-degree corners, the red quadrilateral is a rectangle, and so being a rectangle with diagonals at 90 degrees, it has to be a square. So we've now proven that the inner area, the inner quadrilateral, the red quadrilateral, is a square. And being a square, it has length C. So now we move on from there, that we have a length C on each side of that red square. And now comes an interesting part of the proof where we color the internal red square with green so that we can keep track of the area within. That area, remember, is now C squared, C times C. And I'm going to proceed to break up this area by performing several transformations, which were in previous lectures. We discussed transformations. I'm only going to be using translational transformations, and I want to go through them each, and then I'll walk you through what each translation is. For the visual effect, I'd like to just perform the transformations. There's 3 of them in a row, and then you'll see the result is that the green area gets broken up into 2 other squares. The first one is going to be that lower right corner being shoved up to the upper left corner. and then the upper right corner drops to the lower right corner, and then the lower left corner shifts over to the lower right corner. We're going to detail the translations that break this green square area into two separate square areas. There are three of these translations. The first one is doing the transformation from G in the corner to G prime. So you'll see that G in the lower right corner moved to the G prime that's now in the middle of the green field. That translation between those 2 points was that it shifted in x minus 3 and then shifted in y plus 4. So the translation vector notation is this capital T, stands for translation, with a subscript showing the change in x and the change in y. Another perhaps more familiar notation is the rule notation, where the point xy is mapped to, that's what the black arrow to the right means, mapped to the point xy, and in the case of G, is mapped to the point x minus 3, y plus 4. And so the point is shifted to the left 3 and up 4. The next transformation is dropping the upper right triangle from point E to E prime. And that transformation is given by a zero shift in x. There's no change in the x between E and E prime, but there's a drop in y of 3. So that notation is capital T subscripted 0 change in x minus 3 change in y. Or again, by the rule notation, the point xy goes to x plus 0, no change in x, to the point and y minus 3. And the last transformation was from that lower left corner to go over to the lower right corner, from O to O prime. And that transformation is written as the following. There's no change in y. There's a change in x of 4. So the O goes to O prime by marching across the x-axis 4 places. That corner moves over to the right 4 places. And there's no change in that triangle in the y direction. So now we've broken up the green area, previously green area that was c squared. And we broke it up into two separate square areas. We had the area of the original green, length times width, was c squared. It's been divided into two squares. The first one, the lower left green square, is now the area is equal to length times width is equal to a squared. Got two sides of a. The second square is length times, the area is length times width, and so that's b times b, which is b squared. So the relationship has to be then, those are isometric translations, they didn't change the dimensions or the angles, so the areas didn't change in shifting those triangles around. So the original green area has now been divided into a squared plus b squared. The original green area, c squared, has been divided into two squares of a squared and b squared. So that is the proof of Pythagoras' theorem right there visually. Now within the larger blue square, we have the two white rectangles remain in this configuration. And they have area length times width of a times b. And notice the sides on these white rectangles inside the blue square are a times b. So if we add up the total area of the blue square, we have the a squared lower left green area, we have the b squared upper right green area, and then we have two of these white triangles that have the area a times b. So in total, the whole area can be added up as a squared plus 2ab plus b squared. And we can verify that using the area formula and a little bit of algebra. So if we look at the length of the sides of the blue square, as we had pointed out going around this thing before, was a and b. So we have the length of each side is a plus b. So if we square that with using the area formula, we have a plus b times a plus b. And so we use FOIL from algebra, first, outer, inner, last multiplication procedure for multiplying two items in parentheses. And we get a squared plus 2ab plus b squared. So up above you have the sum of the total area inside the blue square represented geometrically, visually, and down on the lower right you have that same area added up with algebraic multiplication. So we've just proven the Pythagorean theorem. The formula, again, is a squared plus b squared equals c squared. And we've already been using this in the distance formula. And we will see in the next lectures that the Pythagorean theorem helps us to define a circle.